This video is going to be a look at resistance in a wire and what affects the resistance of a wire. And it'll be a submicroscopic model of electric current. So looking at the actual particles moving around and making a link between those particles that are moving in the wire and the amount of current in the wire. So to start with, let's take a closer look at the resistance of a wire. So if we were to talk about a wire, you say, hey, what affects the resistance of a wire? And so if you think about it, you'd say one of the first factors that you would say is got to be what it's made out of. Right. You know that obviously we make wires out of conductors, but if you think about it, like, and you look at wiring around your house or any kind of wires you've experienced, what do they typically make those wires out of that you're going to run current through? And if you peel away all the plastic, insulation around them, typically you see that those wires are made out of copper. Copper is a material that lets charge flow through it relatively easily. There are better conductors than copper. For example, silver and gold are like really great conductors, but obviously they're more expensive, and so we can't, typically afford to make wires out of those. Some like high-end, like stereo components and audio components will have like gold connectors, like gold-plated connectors and such. I've always kind of wondered whether that's more for putting some glitz and glamour on it rather than and trying to sell on that rather than actually being effective. But if you think about power lines, like the power lines that go from a power plant like all the way miles and miles to people's neighborhoods carrying all that electricity, you say, what are those big, huge cables made out of? Well, it turns out that copper, while it's not as expensive as silver or gold, it still is relatively expensive compared to just steel. So even though iron, I know you think about steel and iron as being a metal, and you say, oh, that's a good conductor of electricity. But compared to copper and silver gold, not a very good conductor at all. It's kind of difficult for charges to flow through that. It generates like a lot of heat when those charges are trying to flow through. I've heard it said before that something like a fourth of all the electrical energy that we produce, like power plants, gets wasted just trying to shove the electricity down the wires. So why do we use steel? Well, it has to do more with strength and of a steel alloy versus copper, and maybe perhaps I wonder if resistance to corrosion plays a part. But then just the fact that copper itself is pricier too. So we typically make those power lines out of steel alloy. But like I said, a wiring that typically in homes is oftentimes made out of copper. Okay. So anyway, so what it's made out of, the property of a material that says how difficult it is to put charge through that material is called the resistivity. Okay. Okay, so that property is called resistivity. So the resistance of a particular wire, how difficult it is for charge to get through this particular wire, depends on the material and how well that material, how difficult it is for charge to go through that material, is called the resistivity, which we give the symbol lowercase Greek letter rho. Okay, and you say you've seen that symbol before. We've used it in the past for like volumetric charge density or the volumetric mass density, but we're using this symbol in a different way here. It's a property of material that says how difficult it is for charge to flow through it, to measure that. So the more resistivity a material has, the more resistance a wire made out of that material will have. So we would anticipate that the resistance of a wire will be directly proportional to that resistivity. Okay. A second property, you say, well, let's take a look at this. Say I have a couple wires, and one wire looks like this. Right, I'm trying to move current from here to here, move charges from there to there, and say another wire looks like this. It's a big, thick wire. Which one do you think is going to be harder for the electrons to flow through? The skinny wire or the fat wire? It's going to be harder to go through the skinny wire. Electrons don't want to be jammed together, right? They repel each other. It's harder for them to squeeze through the little wire than the thick wire. So what matters here, I'm going to describe this thickness of the wire in terms of cross-sectional area. Okay, so we'll say the cross-sectional area. And so I'm going to go ahead and give that symbol capital A for cross-sectional area. So again, as the area gets bigger, the resistance of that wire gets smaller, right? So these are not going to be directly proportional. They'll be, it turns out, inversely proportional. I'm going to go through a derivation of this in a bit, but it's going to be in inverse. And then the third property that we want to be concerned with here is going to be if I want to move charge, say from this location here to this location here, move charges from A to B, and I have a choice of taking them through this wire to get there, right? Or taking them through this wire to get there. You say, well, this wire, the electrons have to wiggle and jiggle their way through a whole lot more material than taking this wire. So the difference here is the length of the wire. And so we're going to use a script elder for that. And so you say, so the longer the wire, the more resistance it has. This will also, it turns out, be a direct relationship. So be proportional to L. So if I put those together, then you're going to get that my resistance should be proportional to rho L over the cross-sectional area. And it turns out it is, in fact, exactly equal to that. So this is a formula for giving you the resistance of a section of wire. All right. Now, it turns out there is one more property here, one more thing that's going to affect the resistance of a wire, okay? But it's sort of hidden inside one of these other variables, and that is the temperature of the wire. It turns out the temperature of the wire is going to affect the resistance. Now, the way it does, though, is it does that by modifying the material, right? The hotter it gets or colder it gets, going to change the way the particles in that material are moving. And so it's going to get reflected in this rho value, okay? So this rho value, the resistivity of the material, depends on the temperature that that material is at, okay? Okay, for most materials, do you suppose that will it be easier or harder for charges to flow through the wire as the temperature goes up? So as the wire gets hotter, is it going to be easier for electrons to move around in it or harder for electrons to move around in it? Take a second and kind of develop an opinion. Which way do you think it's going to work? Well, it turns out that the resistivity of a material, it turns out it is, for most cases, directly proportional to the temperature. So it turns out as the temperature goes up, the resistivity goes up, it gets harder for charges to flow through the wire. And you might wonder, hey, why is that it's harder for charges to flow through a wire as it gets hotter? And for that, I'm going to refer you to a little MECU clip.
Under the influence of an electric field, electrons move through a metal much as a marble falls through a viscous fluid. If it weren't for resistance, they would accelerate freely, like a falling body in a vacuum. But as it is, they move on the average at a constant speed. Resistivity is like viscosity. The more of it a material has, the slower a particle will move through it. But what slows the electrons down? In other words, in a conductor, what resists the flow of electricity? Inside a metal, electrons constantly move in all directions. Here, just a few of them are represented as dots. They orbit through the metal as if it were one giant molecule. This kind of flow encounters no resistance, nor does it create a net flow in one end and out the other. Under these conditions, the conductor is in electrostatic equilibrium. There's no electric field inside, no voltage difference from one end to the other. But if a battery makes an electric current flow, equilibrium is destroyed, and an electric field is created inside the conductor. Inside a perfect crystalline metal, if a sample of it could be found, the mobile electrons would continuously accelerate, like a penny falling in a vacuum. But in the real world, crystals aren't perfect. They have defects and impurities, and their atoms vibrate with thermal energy. Electrons, accelerated by the force of the electric field, bounce off each imperfection, behaving somewhat like a ball in a pinball machine. All that bouncing, all that stopping and restarting, produces the resistance that prevents the electron flow from building up speed. So the electrons move at a constant average speed, creating a constant current under the influence of a constant force. As the electrons bounce off the imperfections, they set the atoms into larger vibrations. So the electrical energy of accelerated electrons turns into the heat energy of vibrating atoms.
So taking a look at that clip, you say, hey, I can see that as the wire gets hotter, the particles in the wire are going to wiggle and jiggle more, and that makes it harder for the electrons to find a free path through the material. And so as the temperature goes up, it's harder for charge to flow through the material. The rho goes up, which makes the resistance go up. And so that's that effect. Now, what this means is that when you go ahead and you take a circuit and you go ahead and you flip the circuit on, you know that over time the wires heat up, don't they? And that means over time the resistance is changing. If the resistance is changing, that means that in that circuit, if I use Ohm's law, that means if the resistance is changing, it's the same battery, same voltage hooked up, I'm going to have a changing current. So the current won't be a constant value, right? To make things even more strange, it turns out that Ohm's law, not all materials obey Ohm's law, right? We said before that things that do, we'll call them ohmic materials. Some of the materials don't obey Ohm's law. In fact, there's some materials that as you apply bigger voltage to them, it lets more electrons in the material start to move, ones that couldn't move before. And so you actually start getting current increasing at a different rate. And so Ohm's law is not like this big, huge, overarching law of nature, always true sort of thing. Ohm's law is a lot like Hooke's law for springs. Do you remember that Hooke's law for springs only applies to some springs and some stretchy things, and even if it does apply to them, it's only over certain small stretches and crushes, right? Because then like the string stretches out and you start having to actually stretch the metal, or crush the metal and crush the coils together. You say, well, with Ohm's law, same thing. It only applies to some materials, and even those materials that it applies to, if you start running too much current through it, the wire is going to actually start to heat up and it's going to change the resistivity and affect it. So again, it's something that's good for over like certain like temperature ranges. Most materials, like I said, as you heat them up or cool them down, it'll change that rho value. So Ohm's law, like I said, it's not this big, huge law of nature, but it's a very nice guideline to start from. It's like kind of like you have this ideal and you look at how much it deviates from ideality, right? And go from there. Kind of like with gases in chemistry. I think you talked about ideal gas law, and you talked about gases and how they their behavior diverges from ideal gas law, I think. All right. So that's the resistance formula for a wire. Let's real quick take a look at one last thing with this before I move on to the microscopic model of current, and that is, hey, let's say you can imagine you had a problem like this on the AP. Maybe you have two wires, and they want you to go ahead and do a comparison. And they say, okay, let's say case A here, right? Say that wire looks like this. Okay, that wire has a cross-sectional area A and has a length L, right? And then say case B, we have a wire that has a cross-sectional area of A over 4, and it has a length of 2L. Okay, and the question is, how does the resistance of wire A compare to the resistance of wire B? So in other words, what's that ratio of RA to RB? And so what I would do is I would go ahead and I would take my resistance formula. R is rho L over A, right? And we're assuming these are made of the same material, so the same rho value. And you say, well, what are the changes we're making here, going from case A to case B? You say, well, the changes we're making, we're taking the area and making it 1/4 as big. We're taking the length of the wire and making it twice as long. Now this rho we're not changing, right? It's the same material. And so if this stuff changes, something's got to change to balance it out. Rho's staying constant, so we've got to change the R. So if on the right side we got a 2 over a fourth, over here the new resistance will be 2 over a fourth times the old resistance. 2 divided by a fourth, divided by a fraction, multiplied by the reciprocal. My new one is going to be 8R. So RB is going to be 8 times bigger resistance than RA. So this ratio, RA to RB, is going to be 1 to 8. Right? You can see how they'd write a problem like that. Okay, moving on. We'd like to go ahead and take a look at the submicroscopic model for electric current. In other words, what's happening in that little wire, okay, as the charges flow down. What I want to do is I want to relate the motion of charges in the wire to that overall current in the wire. It's the first thing I'd like to do. So if I have some wire, right, and say in that wire there's all these little charges moving. Okay, now the first thing is when you go ahead and you flip the switch on a circuit, right, as you saw in the MECU video, the electrons aren't all sedately, serenely moving along in nice straight lines through the metal. In fact, they're bouncing all around. So here, like, might be the path that some charge makes. As it goes down the wire, it's going to be going like ping, 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 bouncing off stuff, ping, 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 ping. And so that particle is moving really fast, right? But how fast is it actually flowing downstream? A lot slower. That velocity that they drift downstream with is called the drift velocity, v sub d. Okay, that's my drift velocity. The actual speed of the particles is really honking fast. These little electrons are just zipping around. But the velocity downstream is really relatively slow. It's in units like centimeters per second, right? Is how fast the current is actually flowing down the wire, right? The particles are moving like ridiculously fast, but how fast on the whole, they're moving downstream, relatively slow. All right. So what I want to do is I want to relate the motion of these charged particles in the wire to the current. So if I'm going to do that, you say, overall, I know that current, right? My goal is to get an equation for current. And you say, okay, well, I know that current is my charge per time. So it'd be like dq dt. Let's just write that as an average for right now. I'm just going to do I bar, if that's okay with you. And you'd say, okay, well, that would just be the amount of charge that flows by per time, right? Okay, so charge per time. Okay, that's what I want to end up with. Okay, so I want to cobble that together and I want to relate it back to the motion of these little particles. So let's define a few terms that'll be helpful. First of all, if I take a chunk of metal, right? We've talked about the idea that in these metal atoms, we talked about how the outermost electrons are far from the nucleus and they're not held onto very tightly. But it turns out when you talk about the electrons that are actually free to move from atom to atom, right? They're actually drifting along, called the conduction electrons. You say it turns out that's usually not even like 1 electron per atom. It's like less than that. Okay, so it's a very small fraction of the actual electrons in the materials that are free to move down the wire. So if I went ahead and I kind of diagrammed out here, and I took a little chunk of this wire, right? A little volume of this wire. There would be a certain number of these charged particles that are free to move. Now, in a normal wire, of course, we're talking about electrons that can move. But you know that any case where we have charged particles moving, right, we have electrical current. So we could have, like, say, maybe this is a tube that's filled with an electrolytic solution, right? That's got a bunch of ions, positive, negative ions dissolved in the water or whatever. And if I apply a voltage, right, then it'll make an E field in the wire, and that'll push the positive ions one way and the negative ions the other way. And so I'll get both charges kind of flowing in this. For our purposes today, we're just going to talk about like one type of charge particle. But realize that in a fluid, it could be positive ions moving or negative ions moving, or more likely a combination of both. And a nice example of this is gel electrophoresis. If any of you have taken AP Bio, I suspect you did a little bit with this, or you definitely do this if you take genetics, is you set up a gel electrophoresis experiment where you have this this box and it has this gel, and you like inject in little samples of I think DNA, okay, of different materials, and you apply a voltage, right? And that DNA you've done things to, so it's ionized, and then it's going to start moving and migrating through that gel, right? And as it does it, it's kind of dyed and kind of leaves like these trails. And you can see how far it migrates through the gel. It tells you something about how big and heavy the molecule is, or a fragment, or whatever you're pushing, and how highly charged it is, how far it's going to get pulled through that gel. But anyway, point is that we can have different things, positive or negative, that are moving. Now, what I'm going to do is I'm going to say, in a particular volume, a particular amount of this material, though, there'll be a certain number of charged particles. So there's a certain kind of like charge, these charged particles we call charge carriers, okay? So charge carriers are what we call these charged particles. In a wire, these are electrons, right? But we can have any kind of charged particle would be a charge carrier. We could have ions in a fluid. We can have charged particles in a plasma. We could have someone that's, we have a particle accelerator. We're talking about how many ions are getting accelerated through this particle accelerator per second. But anyway, the charge carriers can be all kinds of different particles then. It's not always electrons is what I'm saying. So what I'm going to do is I can talk about how densely packed those charge carriers are. So in like a certain volume of this material, how many charge carriers I have per volume. I'm going to call that the carrier density. Okay, which I'm going to give the symbol N. Oh, heck, we'll give the symbol N. Okay, that's my, and what that is, that's my charge carriers per volume. It's a good thing you can hear me because no one can read that. And so I'm going to start with that. So I want to say, hey, my current, I want to use this. All right, that's a step along the way to getting to charge per time, right, is to have charge carriers per volume. Okay, but I'm going to have to do something else. So you say, well, I want to get to, not from charged particles, I want to get to just charge. And so I care about how much charge each one of those particles is carrying on it. If it's an electron, each one is carrying an elementary charge, right? 1.602 times 10 to the negative 19 coulombs. If these were like calcium 2 plus ions, each one would have 3.2 times 10 to the negative 19 coulombs, right? So what we care about is the charge per charge carrier. How much charge each charge carrier has. That's going to be Q. That's the charge per charge carrier. That's the charge of the carriers. So if I do that, charge per charge carrier, you say, hey, charge carriers, charge carriers. Now I'm at charge per volume, but I want charge per time. Okay. So the way I'm going to get time involved, right, is I'm going to use this drift velocity guy. Because you say, what's velocity? Isn't it distance over time or displacement over time? And so you say, okay, so if I throw drift velocity in there now, right, that velocity, that's going to be distance over time, or if you like, the length that goes along the wire here in a certain amount of time. Okay. And you say, okay, that got me the time I want. Here's the charge I want. Here's the time I want. But now I have this length here and this volume here I've got to get rid of, right? So I say, well, wait a minute. Here was charge carriers per volume, right? For this volume, right? You say, well, how do you calculate the volume of this? Wouldn't it be the cross-sectional area times the length here? Yeah. So if I go ahead and I replace volume here, right? I'm going to replace that with cross-sectional area times length. Then this length on the bottom is going to cancel this length on top. You see, but now I still have charge and area and time, right? I'm replacing volume with this. So I need to get rid of the area. And so I'm going to multiply by the cross-sectional area of the wire too. Okay. And when I do that, right, it's the area, and the length. Okay, when I do that, I'm just left with charge over time. Okay, this is times. Okay, so that's it. So what I'm getting here is that current down a wire can be expressed as the charge carrier density, charge carriers per volume. I'm going to rearrange the order here if that's okay. Times the cross-sectional area of the wire, times the drift velocity of the particles in the wire, times the charge for each charge carrier. So I have this one in my head memorized as NavQ. Okay, I don't know why. It's just the way I have it memorized. NavQ is my current in a wire. If you look on the, so that's the way I like to think about it. But if you look on the AP formula sheet, on the green sheet, you'll find that they write it slightly differently. On the AP formula sheet, let's see, they write the formula as never. Okay, so they write it on the AP sheet like this, and you say, okay, well, that looks really similar. The only difference is here, right? Okay, the same variables, except this one. What's that taking the place of? That E, that lowercase e? That's taking the place of Q, because what this E is, that's an elementary charge, right? Which, do you remember what an elementary charge is? It's the charge of a proton or electron. That's 1.602 times 10 to the negative 19 coulombs. Okay, and so this formula they have on the AP sheet, that's assuming that your charge carrier is an electron or a proton, something with a charge of +1, you know, of one elementary charge. I prefer to write it this way. This is the way that it works if you have like other charged ions flowing in your water, or in your liquid rather, in your conductor. You could have like, you know, like I said before, like calcium 2 plus ions, or you know, whatever kind of ions you want, that the charge isn't just plus or minus one elementary charge. So that's the deal there. Okay, but this is a better way of thinking about it, I think. Okay, where we want to go with this next. Okay, as we have this formula now, again, it's on the green sheet. All right. we're thinking about, so this is trying to relate current on the big scale to what's happening with little particles moving, drifting down the wire on the small scale. Okay, and linking from one to the other. So where I want to go from here is I want to relate this stuff back to resistance now. All right. So to do this, I'm going to go ahead and introduce a new vocabulary term, and that is current density. Okay, the current density, we use the symbol capital J for. Okay, and what that is, it's easier to just write the formula than think about what it means. You say, hey, the current density, that's my current per cross-sectional area. Okay, so it'd be in units of like amps of current per square meter of cross-sectional area. What that is, it's like how tightly packed you can make the current going down the wire, right? So I could think about having a wire like this, right? And I can talk about, you know, how much charge is flowing down that wire, right? How many coulombs per second per unit of cross-sectional area. You know what I mean? So like for every little 1 square unit, right, in this cross-section, right, how much charge is flowing through that square each second, right? My charge per second per area, right? Charge per second per area. And you say, I can imagine maybe I hook a same wire, and now I hook a bigger battery up to a higher delta V. It's going to be a stronger E field in the wire, which will push more charge per second through. And you say, so I'll be getting, you know, maybe more current through, and it's more densely packed, that current flowing down the wire, and I get more per cross-sectional area. Okay, so that's kind of the idea there. So a lot of in more advanced physics classes, they tend to use current density a lot and do their calculations in terms of J rather than in terms of I. But as they're looking at the physics of things in wires and flowing. But that's kind of a little more for another time. But we're going to go a little more, do a little bit more here. So one thing that I said made sense is I said if I have the wire and I hook up a bigger battery with a bigger delta V, right? And it's going still from connected to the two ends of the wire. So when I go and I do this business, right? You say it's the same length wire, but it's a bigger delta V. Well, it's got to be a stronger E field then, doesn't it? Right? And so we said with a bigger delta V, it makes sense I'm getting more current. Aren't I going to get more current density through that same cross-sectional wire? You say, yeah, same cross-section, bigger current because bigger volt. It makes sense, right? And so there's an equation or relationship that you can write. Okay. Some people like to write it like this. J, that current density, it's going to depend on how strong of an E field you have set up, right? The stronger the E field, the more we should have, right? So it's going to be a direct relationship for most materials, right? The constant of proportionality, J is directly proportional to E. The constant proportionality you can write, one way of writing it is with this guy, okay? You recognize the symbol as a lowercase Greek sigma. Before we use that for like surface charge density or surface mass density, now this is going to stand for something called conductivity. Okay. Now it turns out, what's conductivity? It turns out that conductivity is just the inverse of resistivity. Okay, so resistivity, you remember, is a measure of how difficult it is for charge to flow through a material. So conductivity is how easily charge flows through a material, right? So if like something had a really big resistivity, it would have a really small conductivity, right? But they're in fact just inverses of each other. So I could write the same equation, rearranging this mess. The way it appears on your AP formula sheet is that E is rho times J. Okay, take a second, do that substitution, and rearrange and logic through that this is what you would get. Okay, so this is the way it appears on the AP formula sheet. Now, why do we care about this? Well, because again, it's letting us make a link between electric field strength that we've been studying and talking about how we calculate and doing all these calculations with, connecting that to that flow of charges in the wire, to that current density, how much charge per cross-sectional charge per second per cross-sectional area. So again, this equation actually is the actual true Ohm's law. Not every material will have a direct relationship between E field strength and current density. As like I said before, some things you start put a big enough, strong enough E field in them, a high enough delta V, and then you can start yanking extra electrons out of those atoms, and you'll get more electrons moving, right? And so it won't just be direct proportional. It'll be because you're suddenly putting extra charges in that weren't there before. It'll shoot up in a different way. And other things we talked about, how as I set up a different voltage, about how that's going to like heat the material more as more charge moves, which then affects this kind of feedback circuit. So the point is, things that obey this relationship, nice direct relationship between current density and E field strength, we said those are ohmic materials and they obey Ohm's law. And this is the actual real Ohm's law. We always, people talk about delta V as IR as being like an Ohm's law thing, but in reality, this is the real Ohm's law. Is this. So what we're going to do is we're going to go ahead and relate this back to this, right? If I went ahead and I looked at a chunk of wire and say that this wire, I'm going to have my current flowing to the right, that means I must have an E field set up that way, right? So there's an E field set up in this wire, all right? This wire of length L, right? And say that I know I've measured my delta V, okay, going from here to here, right? I measure what that delta V is. Now, if I go ahead and assume it's a nice uniform wire that has a nice uniform E field in it, right? Nice constant E field strength all the way along the wire. Then for this calculation for the delta V of the wire, right? Isn't it true that that delta V would just be negative and the E would be constant? It would kick out. The dot is just, we're going to go nice and parallel along the wire, right? The E field lines go typically preferentially along the wire, down the wire. And this that integral of dr, that's just adding up all little lengths, dr, that's just the total length of the wire. Okay, I'm going to go ahead and not worry about the negative sign for now. So my delta V is going to be basically E times L. All right, so here I have a relationship for E, right? So what I'm going to do, yeah, let's do this. So the E, you say, I could rearrange this and say it's going to be delta V over the length of the wire, yeah? Okay. I'm going to go ahead and substitute that in here where it says E field. So if I do that, right, I'm going to get the potential difference, the voltage from one end of the wire to the other over the length of that wire, right? The rho is just, let's see, rearranging this mess, you say, well, I'm just going to leave that as rho. Why would I mess with that? That's rho. And the J is the current per area, right? Yeah. That's my current density. Okay. And so if I rearrange this, check this out now. I'm going to move the L over. Look what I'm going to get. I'm going to get delta V is rho L over A, right? Times I. Yeah? Hey, what's this? Rho L over A. Delta V is I times this. You say, wait. I remember that. That's the equation that everyone talks about as being Ohm's law. Delta V is I times R. Delta V is I times this thing. Oh, look, rho L over A. That's our equation we got for resistance before, that we just kind of logicked out, right? But now here it is actually derived, okay, from the equations for path integral for delta V and the relationship between current density and E field strength, right? So this is just delta V is IR. So people talk about this and they call that Ohm's law. In reality, this is the real base Ohm's law, is saying that the E field strength is directly proportional to the current density, okay, for those materials. That's it. So that's a derivation for Ohm's law. One more thing I should talk about just as a side note here, okay, before I wrap up this video, and that is that there are some other materials that don't really follow the normal relationships for resistance and temperature, and those are things that are superconductors. So just a little FYI on superconductors, okay? So most materials, okay, I think we commented on that before, that the resistivity is a function of temperature, right? And we said that resistivity depends on temperature, and that most materials, as you heat it up, as you increase the temperature, the resistivity goes up, right? And so the conductivity would go down, right? If you want to write it like that. So, but if I made a little graph and I said, okay, let's say that this is the temperature, okay, and I'm going to do it in kelvins, right? And then this is, we'll say, the resistivity of the material, or the resistance of the chunk of wire, your choice. We'll say the resistivity, okay? Most materials would follow a graph that looks something like this. Hey, when the temperature is high, the resistivity is high. When the temperature gets low, the resistivity gets low. And the graph will be relatively linear for most materials. We'll give a nice linear plot. But there are some materials that will follow a plot that looks like this. And then all of a sudden, it'll drop to 0. So they'll be following along like usual, and then all of a sudden you get to some magical temperature, right? And all of a sudden, the resistance actually goes to 0. And so suddenly you have a wire that has no resistivity, so charges can just flow through the wire without losing any energy at all, and they don't slow down the charges moving at all. A material like that's called a superconductor. Okay, superconductors were discovered a long time ago when they first started being able to get materials like super cold. When they were first figuring out how to do that, the guy that was doing the research on that, some of the first pioneering research on cooling things down really cold. His last name was Onus, right? It's like Heike Onus, and he made the discovery that if you took liquid mercury, the stuff they used to put in thermometers, the silvery metal, liquid metal, when you cool it down enough, of course, it's going to go to solid. But you cool it down enough, and by enough, it's around 4.2 kelvins, right? So you say, well, let's see here. Absolute zero Kelvin is negative 273.15 degrees Celsius. So this is very roughly negative 269 degrees Celsius. When it gets that cold, just 4 degrees above absolute zero, right? Cold as anything can be, it suddenly became superconducting. That's the first superconductor discovered. Since then, they found different materials that are superconductive at higher and higher temperatures, right? Okay, but it was one of the things that was amazing was when I was in high school. Which is the late 1980s, they found a material that would be superconductive at a temperature that was above the temperature of liquid nitrogen. Okay, and that was a huge deal because the way that you keep the wires cold enough typically is you'd put them in some gas that you've cooled down to liquefy, right? That you've chilled. So liquid nitrogen, that most of the atmosphere is nitrogen. I forget what it is, somewhere around, is it around 70% of the atmosphere, I think, is nitrogen? I think somewhere around 70. And so the point is that nitrogen is plentiful. And when you start cooling down the air, it's cheap and you can make liquid nitrogen, right? And the temperature of liquid nitrogen is then when you get something that's cold enough to make it superconductive, that's a big deal because now you can relatively cheaply keep these things refrigerated enough to keep them superconducting. And so when that happened, like I said, was when I was in high school, that discovery was made. It's I think it was yttrium, copper, barium, calcium, cuprate. Did I say copper already? Anyway, compound, like a ceramic type material. Anyways, the point is, it was a big deal because now suddenly making superconducting things was a lot more practical, right? And so, like at Fermilab, they had the big particle accelerator, the Tevatron, that they used to accelerate particles up to 99.99% of the speed of light, and then collide them and look at the inner structure of particles. And so the point is, as they when they this material came out, they were like, oh, holy cow, it takes so much energy to run our electromagnets to power that thing and steer those particles. We could actually save money uh, by reinstalling all new magnets in the ring that are superconducting magnets, and using liquid nitrogen to cool them would actually save money. And so they did that, and they reinstalled and did, made a whole, in the ring, basically installed inside the ring, a whole new ring of that's was using superconducting magnets to steer those particles. So the hope that people have is that we would go ahead and find a superconductor, a material that would be superconductive at like normal temperatures, right? Like, gosh, it'd be great if it was something we could just, cool with a normal refrigerator to keep to that coldness. Or, oh my gosh, if it was something that was superconducting at room temperature, that would be fantastic, right? Then in normal conditions, you don't have to do anything special, and you can run charges down it and the wire doesn't heat up, right? There's no resistance to take energy out of the charges to turn to heat, and the charges flow along, so you're not losing any energy in the wires. That would be awesome, right? And I think I said earlier this film, I think I said, hey, I think that I remember hearing something like a fourth of the electrical power generated at power plants gets wasted moving down those wires. If you had superconducting wires, you could save all that energy, right? Be able to use it. So that's a big deal. And there's lots of people who've done research, and they found since, when I was in high school, they found higher and higher temperature superconductors, but they haven't gotten to room temperature yet. And this is one of those things that, I mean, it's maybe a material that's superconducting, like at room temperature. A reasonable material doesn't exist. Who knows? Maybe it's out there, and people just haven't found it yet. But I've heard kind of wacky stories about people trying different things, and like, almost out of desperation, or just what the heck, let's see if this works, and finding superconducting materials like surprisingly, out of components they weren't expecting. So it's I think it's how superconductivity works on the teeny level. I'm going to tell you that anytime you get down to the atomic scale, right? Microscopic into atomic scale, or smaller, and this is definitely smaller, talking about individual electrons moving in wires and stuff, you move into the realm of where you need quantum mechanics to really study and understand it. And in this case, I don't think that superconductivity is really fully understood. I know that there's a theory of superconductivity that was put together by three different physicists, but I don't think that they understand it as well as they'd like. So it's kind of a frontier sort of a thing, is superconductivity. But it's something that people are doing research on, and would be, a room temperature superconductive conductor would like really change the world. It would be another way you could store energy. You could make a circuit and have electric charge flowing and flowing around the circuit, and you wouldn't lose any energy. You could store it that way. Right? It'd be another way of storing energy, instead of like storing it in batteries or whatever. We have to run like a little chemical reaction to store it. It'd be much, much nicer. So could really change the world in a lot of ways if we had good temperature superconductors. The other thing you can do with it, like I was kind of alluding to, is making magnets, right? When you make magnets, you got to run current through the wires to make the magnetic fields. And if you want to make a stronger magnetic field, well, you just run more current through. Well, if you run more current through, then the wire heats up, and then it gets more resistive, and you're losing energy, and yada 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 yada. Run too much, you melt your wires, right? It gets too hot. So they, superconductors could help solve problems with things like that too, let you make better magnets and such.